Algebra 2. This is 10.1.1 and 10.2.1. This is the beginning of chapter 10, which is all about exponential and logarithmic functions. So in this chapter, this is probably the first thing that we're going to be doing that you have never seen any piece of before in Algebra 1 or pre-algebra. I think just about everything we've done this year, you've seen a little bit of it before. And we've taken it to another level and added another twist, and maybe done more with it and taught you how to do more applications with it. This logarithmic and exponential functions, I'm willing to bet you've never seen these before. So in this first section, we're going to be just talking about the basics of these and doing a few operations and some simple things that we can do with them. Now, we're going to cover a lot, and this is going to seem like a lot, but kind of doing all of this in one day makes the rest of the chapter a lot easier. And so hopefully that works out for us. So by the end of today, you should be able to identify and evaluate exponential functions and then use logarithms to simplify and evaluate exponential functions. So I mentioned that we're going to be talking about these two things, exponential functions and logarithmic functions. And they're related to each other. They're actually the inverses of each other. And you can take every exponential function and rewrite it to convert it to a logarithmic function. And you can do the same thing with a logarithmic function. You can rewrite that and convert it into an exponential function. So that's why we do the same. That's why we do them together in one chapter. Now, these graphs right here give you some examples of real-world uses of exponential functions. So world population growth, in the beginning of the fossil record, maybe 2 to 5 million years, or the beginning of when we know man first existed, you can see that we have a very slow growth in population. But then as we get closer to the 20th century, right, it shoots up quite rapidly. And so that's characteristic of exponential functions. They grow very slowly, and then all of a sudden they shoot up pretty rapidly, and they grow quite quickly. And so you can see the same thing here with bacterial growth. If you have bacteria in a petri dish and they double every so often, well, at first it seems like they grow really, really slowly and there's not that much, and then all of a sudden they get there's a lot of them really quickly. And that has to do with, if you think about what happens when a number is constantly doubling, if you take 2 and then double that, you go 2, 4, 8, 16, 32, 64, 128, 256, 512, and you can keep going on and on and on and on. And you can see how in the beginning these jumps are kind of small, but then as you get down here, these jumps are really big, right? So you start off small jumps to big jumps, and then that gives you a graph that looks like these right here. Now, just a quick review to show how these functions relate to some of the other ones that we've recently talked about. We recently did a whole chapter 8, on quadratic functions. And so an example of a really simple quadratic function is x squared is 16. And so in a quadratic function, the base is the variable, right? So in this case, x is your base, and the exponent is your number, okay? Now, in an exponential function, we flip that around, and your base is your number, and then the exponent is the variable. So that's the big difference here, is the exponent is now your variable, okay? So a quick definition of this, exponential functions look like f of x equals b to the x, where b is some number that's greater than 0, right? So it has to be positive, and it's not 1, right? And that's what we have in this example I gave you right here. Your base is 4, so 16 is 4 to the x. If b is negative, the function ends up being an imaginary or complex number for even values of x. So that's why we say our base cannot be negative. So in this first example, example 1 shows you a really simple way that you can work with exponential functions. So here you have to evaluate f of x is 2 to the x at x equals 3 and x equals -2. So you know when you evaluate functions, you just take the value that you're given and you plug it in for x. So I'm going to start off by evaluating f of 3, right? And so I'll just plug 3 in wherever I see x. So then this turns into 2 cubed, and I can simplify that, and I know that 2 cubed is 8, and that's my answer, and I'm all done. So then the next piece is we'll evaluate this for x equals -2, right? So then I plug in -2 wherever I see x. So I have 2 raised to the -2. Okay, so the issue here is we've got a negative exponent. So you know whenever you have a negative exponent, you move that to the other piece of a fraction. So that's why we move this whole thing down below, and then we simplify this, and we get 1/4, and that's our answer. And we're all done. So 2 examples of how you can simplify exponential functions with positive and negative numbers. The next piece, evaluating exponential expressions for irrational numbers, okay? So to evaluate an exponential expression for some irrational number, we can only really approximate the value. We always have to cut off our value at a certain number of decimal points. And so when I'm talking about irrational numbers, I'm talking about numbers that cannot be simplified to a fraction or terminating decimal or repeating decimal. So examples are something like pi, 2 pi, or anything that includes pi, or 2.12927, right? Some weird decimal that just kind of goes on forever and ever and ever and doesn't stop, okay? These are irrational numbers, and so if we evaluate exponential expressions with those, we always have some number of decimal places and we can't cut it off. So in example 2, we're given the function f of x is 4 to the x, and we have to evaluate this at x equals √2. So we have f of √2, and so what I'm going to do is I just plug in √2 for x, okay? And I know, well, √2, that's an irrational number. That's, if you plug that into your calculator, you'll get a decimal that doesn't end and doesn't have any clear pattern. So we just have to cut it off at some point and just approximate. So I'll take 4 decimal places, so I'll do 4 to the 1.4142. I plug it in, and again, I have to cut off my answer at some amount of decimal places, so I get 7.1029. Okay, so nothing too special here, just that we have to cut off our decimal places at some point. So exponential expressions can be evaluated at both rational and irrational numbers, so their domain is all real numbers. When you have an exponential expression, you can plug any number, any real number at all, in for your exponent. Any positive number, any negative number, and 0. You know we can have exponents that are positive, negative, and 0. So for that reason, like we said, domain is all real numbers. Now, because your base always has to be positive, right? And you know that when you have negative exponents, it just turns them into a fraction. The range of exponential expressions is all positive real numbers, okay? So your domain is all real numbers, but your range is all positive real numbers. So then in this example, example 3, we have to evaluate f of x is 1/2 to the x at 2 and -3, okay? So I'm going to start off by plugging in 2 for x, and so I have 1/2 squared. And so just a quick review of fractions, fractions with exponents. You know that if you have an exponent on the outside, that applies to both pieces of your fraction on the inside. So then we could say that f of 2 turns into 1 squared over 2 squared, which is just 1/4. And so then we can do something similar with f of -3. We have 1/2 raised to the -3, right? Now, a really easy way to deal with any fraction that is being raised to a negative exponent is to flip the fraction first. And if you flip the fraction first, then that allows you to make your exponent positive, right? So you can see I flipped my fraction, I made my exponent positive, and then this turns into 2 cubed over 1 cubed, which is just 8. Okay, so your answer there is just 8. And then example 4, we could have exponential functions that are a little bit more complicated, where their exponent includes a variable with different operations on it, and we still just go about things the same way. So for this one, we'll start off with f of 1 is going to be 2 to the 3 times 1 minus 1. So if we simplify that, it'll be 2 to the 3 minus 1, so 2 squared, which is just 4. And then we have f of negative 1. So I'll have 3 to the negative 1 minus 1, which is going to be 2 to the negative 3 minus 1, which is 2 to the negative 4. So, okay, we've got a negative exponent. So then what that means is this is going to turn into 1 over 2 to the 4th, which is going to be 1 over 16. And so that's our answer there. All right, going on to example 5. So we'll have f of 4 is going to be, the square root of 5 raised to the 4th. And so that'll be something that we'll plug into our calculator. So you'll just do root 5 as though you normally would, right? And then, so what I punched into my calculator is I did the square root button and then 5. I closed the parentheses and then I hit enter. And then what that gave me in my calculator is that gave me gave me 2.23606, and it goes on forever and ever and ever. Now what I have to do is I have to raise that to 4. So I'm going to do second and then answer down at the bottom, right? So I push my second button, which is in the top left corner, and then there's a button at the bottom of the calculator in the bottom row, and you've got a minus sign in parentheses, and then above that is the word A and S, and then you push that, and what that does is that refers to your previous answer. And then there's a button on the right side of the calculator. It's the caret that you use for exponentials, right? So this is on the right side. So you can use that caret to throw in any exponent. And so we want to raise all of this to the power of 4, right? So then I do 4, and then I hit enter, and my answer is 25, right? So that one was pretty nice and easy. So let's do the same thing. We'll run through the same process, push the same buttons for f of negative 2.1. So f of negative 2.1 is going to be the square root of 5 raised to the negative 2.1, right? And then if I use the correct negative, I can just punch this into my calculator. So let's see, I'll do square root of 5, close the parentheses, and then your caret button on the right side of your calculator for your exponent, and then negative 2.1, right? And so that'll give me the answer of 0.18. I'll round that, I'll round that to 3 decimal places. I'll say 0.185. Okay, and then the last piece, x is pi, so we'll do f of pi, which is going to be the square root of 5 raised to a pi. So I punch in pi, and then I do my caret or my exponent button on the right side of the calculator, and then for pi, you can press second and then your exponent button, which has pi on top of it, and that'll give you 12.5296. So we'll round this to 12.530. Yeah. Okay, so to find pi, if you need to do this again on your calculator, pi is just the second button and then the exponent button on the right side of your calculator, and you can see on top of that exponent button there's a little symbol pi. Okay, so that's how we get to that. All right, so that's an example of how to deal with exponential functions when things aren't so simple and you've got decimals and other types of irrational numbers. Now, exponential functions, these include the number e. So this is a tricky thing about this. e is a number, or lowercase e for that matter. And so if you think about, as we've gone through this textbook in Algebra 2, in your course in Algebra 2, we've never used lowercase e as a variable, because that is a very specific number. We use that for, it's a specific irrational number that's used in exponential functions, and it's approximately 2.718288183, and this actually goes on forever and ever and ever. It's a non-terminating and non-repeating decimal, okay? And so there is some way that we've gotten at this number and some very specific meaning to this, but it's kind of beyond the scope of this course. So to save time, we won't go into that. But what you just need to know is that e is approximately, for your sake right now, e is approximately 2.718. But you don't even have to remember that, because there's an e button on your calculator. So the e button, if I look at my calculator, it's the second, you press your second button, and then the division sign, right? The division sign, which is 1, 2, 3, 4, 5, which is fifth from the bottom on the right. 1, 2, 3, 4, 5. Yeah. Okay. And then that gives you e. And so then if you hit enter, you can see your calculator gives you 2.71828, so on and so forth. Okay. And so we can use that to evaluate e at different values. So in example 6, we have to find f of x equals e to the x, and we're going to start off with x equals 2. So f of 2 is just going to be e with 2 plugged in for x. And if I punch that into my calculator, right, and I can do the caret button on the right side of the calculator. Whoops. Second e raised to the 2, and so that'll give me about 7.389, right? So I cut it off at 3 decimal places. And then I'll do f of -3, which will be e to the -3. And then same thing, you can just punch this in using your calculator. So when you do use your negative, make sure you use the negative on the lower right of the calculator. And we're going to get 0.49787. So we'll round that. If we round that to, oh, wait a second, I put my decimal point in the wrong spot. It should be 0.049. So if we round this to 3 decimal places, let's see. Well, the third decimal place will be cut off right here. So this is actually going to round to 0.050. Okay, and then we'll do f of pi, which is going to be e to the pi. And that'll give us 23.141. And that's it. All right, moving on to talking about logarithms. So a logarithm, that's the inverse of an exponential function, and you can take any exponential function and convert that to a log function. So if x is positive and b is some positive constant that's not equal to 1, then if we have y equals log base b of x, if we start off with y equals log base b of x, we can take that and we can convert it to b to the y equals x. And so this right here, this statement right here, might be the biggest stretch for this whole entire course. Okay, and so let me just take a step back and go over that again. So we have y is log base b of x. So log right here, well, log is a piece of wood, but it's also a very specific math function. It means logarithm, and it has to do with powers of 10. And so whenever we have a log, we have this little number down here right now that's being represented by b, and so that's a subscript, and it's always written a little smaller and slightly below. And then you have your argument, which is x, and that's written in a normal size and a normal height, after your base. And then the whole thing equals y, or your answer. Now, everything you have right here, you can take that and convert it to an exponential function, which is also called the antilog, right? So the exponential function of every logarithm is called the antilog. So if I were to take this y equals log base b of x and can convert that to an exponential function, well, I have a base of b, my exponent is y, and then that all equals x, right? So your base, how I always remembered it was the base of your log is the same thing as the base on your exponent, okay? So the base of the log is the same thing as your base on your exponent. So that goes there. Your answer becomes your exponent, right? And then your argument just drops right down. Okay, so I'll show you that one more time. So if we have y equals log base b of x, that's going to turn into, you have your base. Actually, let's refer to this with some different words. Let's say exponent equals log of the base of your answer, right? So this is going to be, you have your base and then raised to your exponent, and that all equals your answer. Okay, so if I look at these examples right here, these are equivalent exponential and log forms, right? So my exponential form, 2 to the 4 is 16. Well, if I can convert that to log form, that would be log base 2 of 16 is 4. And then if I take 2/3 raised to the second power equals 4/9, well, 2/3 is my base, so that goes right after the log. I have an exponent of 2, so that's going to be the answer of my whole log function. And then it all equals 4/9, so 4/9 is going to be the part of the argument of my log function. Okay, so then I can even throw some negative exponents in there. If I have 10 to the negative 1 equals 0.1, so that turns into log base 10 of 0.1 is negative 1. And so an easy way to remember this is b to the a equals x. So log base b of x equals a. Okay, and so you can see how you kind of flip things around. So your base always goes beneath your log right there. And so your exponent becomes the answer and always goes on the other side of the equal sign. And then the answer in exponential form always becomes the argument of your log, right? And that goes after the base and before your equal sign. Okay, so you can see we're kind of just, we hold on to our base, but we're kind of just flip-flopping our answer and our exponent. So for example 7, you have to write that in log form. You have 4 to the 5th equals 1024, and you have to write that in log form. So all you're doing here is just flip-flopping some stuff, right? So 4 is your base, okay, and so that goes down there and becomes the base on your log. Your exponent is 5, so that becomes the answer to your log function. And then the answer to your exponential function, well, that just drops right down and becomes the argument of your log function. So then for example 8, we have to write 3 to the negative 4th equals 181 in logarithmic form. So I'll have log base 3 of 1 over 81 equals negative 4. Okay, and so that's just a whole rewriting thing. And so you can see my base dropped right down, and then I just flip-flop my exponent, and then my argument or my answer. All right, so here's another example. Let's say we have log base 7 of 343 equals 3, and we have to write that in exponential form. So we'll take our base of 7, right, and you drop that right down, and that becomes your base here. Your answer is a 3, so that'll become the 3 on 7, and then the argument of your log, 343, well, that just becomes your answer to the whole thing. So now in example 10, we have to write log base 10 of 0.001 equals -4 in exponential form. So my base is 10, the exponent on that is -4, and it equals 0.001, right? So if you want to see how I did that, I dropped my base down, my exponent and my answer, or the argument of my log, flip-flop. All right, so a few rules about logarithmic equations. So if we can have logarithmic functions, then we can have equations with logarithms. And so a few rules to go over before we solve these. If your logarithm equations are y equals log base b of x, and then the reverse of that, or your antilog or your exponential, x equals b to the y, then b to the y is always positive and x is always positive, okay? The logarithm of a negative number is not a real number, okay? So we can't have those. And so then we have this equality of exponents property right here, and this will come into play later in chapter 10, and we can do a little bit with it today. But what this is saying is that if you have an equation set up and you only have one thing on either side of the equal sign, and you know that that one thing has the same base, then your exponents have to be equal. And so you can set that, you can drop your bases and write an equation where with just your exponents, where your exponents are equal to each other. So, and we'll do a little bit with that today, and then we'll use that more at the end of the chapter. So a few steps to evaluating logarithms. Well, what you can do is you can start off by taking the whole logarithm and setting it equal to x, and then rewriting it in exponential form. And sometimes by doing it that way, it helps you to see what piece you're missing and what the whole thing equals, right? And then you can just solve for x using the equality of exponents property. So my first example, example 11, I have log base 2 of 8, okay? And I have to evaluate that. So my first step to evaluating these logarithms right up here is to set it equal to x. So I'm going to set this equal to x. And then I'm going to rewrite this in exponential form. So my base is 2, the exponent on that is x, and the whole thing equals 8. Right? So just quick reminder, what I did is I dropped my base down, that didn't change, and then I flip-flopped the exponent and then the answer. So now I have 2 to the x equals 8. So now I've got to think to myself, well, 2 to what power gives me 8, right? And I know that 8 is the same thing as 2 cubed. All right, so I have 2 to the x on the left side. On the right side, I have 8, so I could say 8 is the same thing as 2 cubed. So now I have a situation where I have the same base, so I can get rid of my bases and have just my exponents, right? Drop my bases, have just my exponents, and that's going to leave me with x equals 3. So then I can go back up here and fill that into this statement, and we can answer the original problem or the original question and say that log base 2 of 8 is 3. And we're all done, right? And that makes sense because if we were to take this and rewrite this in exponential form, well then we know it would be 2 cubed equals 8, right? My base would drop, and then my answer and my exponent would just flip-flop. All right, example 12, we have log base 3 of 1 over 9. So how I'll start this one, same thing I did. Log base 3 of 1 over 9 equals x. So I'm going to rewrite this in exponential form. So I'll have 3 to the x equals 1 over 9, right? So what I did is I dropped my base, and then I flip-flopped my argument and my answer. So this one's tricky because I have 3 to the x equaling some fraction, some number that's less than 1. But I know, if I think about the connections between 3 and 9, I know that 3 squared is the same thing as 9. So one of the things that I could say here, well, 3 to the x is 1 over 3 squared, right? And so I've got that in a denominator. Which doesn't help me a whole lot. I could put that in the numerator if I somehow flip the fraction. And you can do that if you reverse the sign on your exponent. So I can take this positive exponent and I could move this whole thing up top, but then if I did that, I would have to flip the sign on my exponent. So you're usually used to making your exponents positive and flipping things, and now in this case we've got to make the exponent negative and flip it, right? So then this is going to turn into 3 to the x is 3 to the negative 2. And if you want to put it over 1, that's fine. So then we say, well, we don't really need it over 1. We can just get rid of that. And so then we have an equation with one thing on either side of the equal sign. Our bases are the same, so we can drop our bases and then just write the equation as x equals negative 2, right? So x equals negative 2, and then we can take that and kick that back up here and fill that in here. And then we can write our final answer and say log base 3 of 1 over 9 is negative 2. And that's our whole answer, and we're all done. So let's go on to number 13. We have to solve log base 4 of x, set that equal to negative 2, solve it for x. So we could solve this one by first converting to exponential form. Okay, so my base is going to be 4. The exponent on that is going to be negative 2, and then that all equals 8, or x. And so now what I want to do is simplify this 4 to the negative 2. Well, that's the same thing as 1 over 4 squared, which is the same thing as 1 over 16. So x is 1 over 16. All right, and so that's our answer, and we're all done. So the last thing, solving logarithmic equations. Okay, so that's kind of what we did in number 13, and we can try that again in number 14, so you can see how we solve these logarithmic equations. The big hint here is rewriting them in exponential form. Okay, so for example 14, we have log base 6 of x is 2. So my base is 6, the exponent on that is 2, and the whole thing equals x. So we know 6 squared is 36, so 36 equals x. And that's our answer, and we're all done. So we'll talk a bit about common logs. Common logs are logs with base 10. And if you see a log where no base is written, you can assume that the base is 10. So for example, if we have log base 10 of x, that's the same thing as log x. And you don't have to write your base if it's 10. And so how we can evaluate these in our calculator, there is a log button on your calculator. It's on the left side, 4th button up from the bottom row. Okay, and so that allows you to evaluate common logs or logs with a base of 10. So natural logs, these are logs with a base of e, and so you can use ln for natural logs. And so if your base is ever e, you don't have to write it, and you can just change the whole thing to ln of x to stand for natural log. Okay, and so a lot of students, they say, well, if ln stands for natural log, why isn't it L, and that's because it comes from the French. I think how the French say it is they say log naturel, and so they have logarithm first, or the L first, and then the N for natural at the end. Okay, so the L button on your calculator, it's like on the left side again, 3rd button up from the bottom row. And so you can play around with that and plug different things in for log and natural log. One very important one that you probably should memorize is the natural log of e is 1. Okay? And that makes sense. I can go through that really quickly. So if we have natural log of e is 1, well, we could rewrite that in log form. So that's the same thing as log base e of e is 1. And then if we convert this to exponential form, I know I have a base of e. If I crisscross between my exponent and my argument, well, then I have an exponent of 1, and then that equals my argument of e. So e to the 1 equals e, and that makes sense. Because if you have an exponent of 1, then you should equal yourself. So solving natural and common log equations, how we typically do this is you're going to rewrite your equation in exponential form. Okay, so sometimes changing the form, a lot of the times changing the form helps us see what we have and makes it easier to work with. If you have log and no other base is specified, you'll use a base of 10. If you have natural log and no other base is specified, you'll use base e. Okay, and then you just evaluate and solve. So for example, number 15, we have natural log of x equals -1. So how I would rewrite this, well, let's see, I'll copy down the problem first, and then I'll show you how I would rewrite it. So if I have natural log of x equals -1, how I would rewrite that is I would rewrite this as log base e of x equals -1. So the only thing I've done so far is rewritten it with my base of e. And then I would convert to exponential form. So I have a base of e raised to the -1 equals x, right? So all I've done there is convert to exponential form. So I dropped my base and then I crisscrossed my exponent and my answer. And so then this is something that you can plug into your calculator, right? And so I'll plug in e, which remember is the second button and then the division sign, which has the e above it. And then I'm going to do my caret button, which is on the right side of the calculator. And then I'm going to tell it -1, right? And so when you put in that -1, let's see, raised to the -1, make sure you use the negative down at the bottom of the calculator. That's between the two parentheses, okay? And then 1, and then enter. And then the answer that you should get, 0.367. And actually it's 3687, so we'll say 0.368. Yeah, 0.368. So that's probably the best way to round it and write your answer. All right, so that is it for 10.1.1 and 10.2.1. So I hope that helps, and I hope you can go ahead and try your homework on your own.